Have you ever had a moment where something felt off, like a glitch in the matrix? Maybe you could have sworn you put your keys on the table, but they ended up somewhere else. Maybe you remember a conversation that never happened. Maybe you have experienced that strange feeling of déjà vu, where you are absolutely certain you have lived through this exact moment before. Most of us brush these moments off. Memory is unreliable, we tell ourselves. The brain plays tricks. But what if those moments are something more? What if they are tiny cracks in the code? Little errors in the program that runs our reality. I know. It sounds like science fiction. It sounds like something straight out of the Matrix. But here is the thing. The simulation hypothesis is not just a fun thought experiment anymore. It is a serious area of study. And the more we learn about physics, computing, and the nature of reality itself, the more this idea refuses to go away. So tonight, we are going to explore everything. We will look at the philosophical arguments that have been debated for thousands of years. We will examine the mathematical probabilities that make some scientists genuinely nervous. We will dig into the strange discoveries in physics that seem to suggest reality works more like a computer than we ever imagined. And we will ask the big questions. If we are in a simulation, who created it? Why? And perhaps most importantly, does it even matter? Ready? Good. Because reality might not be. Let us start with the basics. What exactly do people mean when they talk about the simulation hypothesis? At its core, this is the idea that what we perceive as reality, everything from the chair you are sitting on to the stars in the sky, to your own thoughts and memories, might not be real in the traditional sense. Instead, it might all be an incredibly sophisticated computer simulation, created by some advanced intelligence that we cannot even begin to comprehend. Think about video games for a moment. When you play a game like Grand Theft Auto or The Sims, you are controlling characters in a virtual world. That world has rules. It has physics, sort of. The characters in those games can interact with their environment. They can build things, drive cars, have conversations. To them, if they were conscious, their world would seem completely real. Now imagine a video game that is unimaginably more advanced than anything we have today. Imagine a simulation so sophisticated that the characters inside it are genuinely conscious. They have thoughts, they have feelings, they have free will, or at least they think they do. They can ponder the nature of their existence. They can ask questions about their universe. And here is the kicker. They would have absolutely no way of knowing they were in a simulation. That is the simulation hypothesis in a nutshell. The idea that we might be those characters, that what we call reality is actually a program running on some unimaginably powerful computer, created by beings so far beyond us that we cannot even conceive of their true nature. No, this raises all sorts of questions. If we are in a simulation, what is outside the simulation? Who are the programmers? What is their reality like? Are they in a simulation too? Could there be simulations within simulations within simulations, like an endless stack of Russian nesting dolls? These questions make most people's heads spin, and honestly, they should. Because if the simulation hypothesis is true, it fundamentally changes everything we think we know about existence itself. But before we dive into the evidence, let me make one thing clear. This is not about proving whether or not we live in a simulation. That might be genuinely impossible. What this is about is examining why so many smart people think this is at least plausible, and what the implications are if they are right. Here is something that might surprise you. The basic questions behind the simulation hypothesis are not new, not even close. Humans have been questioning the nature of reality for thousands of years. The language is different, the metaphors have changed, but the core questions, they are ancient. Let us travel back about 2,400 years to ancient Greece. There was a philosopher named Plato, and he told a story that has haunted thinkers ever since. It is called the allegory of the cave. Imagine, Plato said, a group of prisoners who have been chained inside a cave their entire lives. They are facing a blank wall and cannot turn around. Behind them there is a fire, and between the fire and the prisoners, people walk back and forth carrying objects. The prisoners cannot see these people or the fire. All they can see are the shadows that these objects cast on the wall in front of them. Now here is the key part. To these prisoners, the shadows are reality. They have never seen anything else. They give the shadows names. They study their movements. They develop entire philosophies about the nature of these shadows. The shadows are, to them, all that exists. But we know better, right? We know the shadows are just pale reflections of a much richer reality. The real things, the actual objects, are behind them. And beyond that cave, there is an entire world they cannot even imagine. Plato's question was simple but profound. What if we are the prisoners? What if everything we perceive is just shadows on a wall? What if the true nature of reality is something we cannot see, cannot touch, cannot even conceive of? Sound familiar? Plato was essentially asking whether our reality might be some kind of illusion. More than 2,000 years before computers were invented, he just did not have the metaphor of a simulation to describe it. But Plato was not alone. Around the same time, on the other side of the world, philosophers in ancient China and India were asking similar questions. In the Zhuangzi, an ancient Chinese text, there is a famous story about a man who dreams he is a butterfly. When he wakes up, he asks a disturbing question. Am I a man who dreamed he was a butterfly? Or am I a butterfly dreaming I am a man? Again, the core question is the same. How do we know what is real? How can we be certain that our waking life is not itself some kind of dream or illusion? Fast forward to the 1600s, and you get René Descartes, the French philosopher famous for saying, "I think, therefore I am." Descartes was obsessed with certainty. He wanted to find something, anything, that he could know for absolute certain. And in his quest, he entertained some pretty wild ideas. What if, Descartes wondered, there is an evil demon who is deceiving me? What if this demon is so powerful that it can make me believe anything? Maybe my body does not exist. Maybe the world around me is an illusion. Maybe 2 + 2 does not really equal 4. But this demon is tricking me into thinking it does. Now replace evil demon with advanced computer simulation, and you have basically the same scenario. Descartes was grappling with the simulation hypothesis 400 years before the first computer was built. The point of all this history is simple. The questions we are asking tonight are not new. They are among the oldest and deepest questions humans have ever asked. What has changed is that we now have new tools, new technologies, and new scientific frameworks that let us examine these questions in ways our ancestors never could. And when we do examine them with modern tools, the answers we get are not as reassuring as you might hope. Now we need to talk about the person who really put the simulation hypothesis on the map in modern times. His name is Nick Bostrom, and in 2003 he published a paper that made a lot of very smart people very uncomfortable. Bostrom is a Swedish philosopher who works at Oxford University. He is not some fringe thinker. He is a respected academic who specializes in thinking about existential risks, artificial intelligence, and the future of humanity. And in his paper, titled, "Are You Living in a Computer Simulation?" he laid out an argument that is frustratingly hard to dismiss. Here is how the argument works. Bostrom starts by asking us to consider the future of technology, specifically the future of computing. Our computers have gotten incredibly powerful over the past few decades, and if you follow the trends, they are likely to keep getting more powerful for a long time to come. Now imagine a civilization that is much more advanced than ours. Maybe a civilization 1,000 years ahead of us, or 1,000,000 years. Given enough time and technological progress, Bostrom argues, such a civilization would eventually develop the ability to run incredibly detailed simulations, not just simulations of weather patterns or chemical reactions, but simulations of entire worlds. Simulations populated by beings with consciousness, with thoughts, with what appears to be free will. These would be ancestor simulations, as Bostrom calls them. Simulations of the past, perhaps created by future humans to study their own history. Or simulations created for entertainment or research, or reasons we cannot even imagine. Given the computational power of such an advanced civilization, they could run not just one or two such simulations, but billions of them, maybe trillions, maybe an essentially infinite number. And here is where the math gets scary. If there is one real universe and countless simulated ones, then simple probability tells us something uncomfortable. The vast majority of beings who think they are in the real universe would actually be in simulations. The odds would be overwhelmingly against being in the one true reality. Think of it this way. Imagine there is one real apple and 1,000,000,000 fake apples that look identical. If someone picked an apple at random, what are the chances they got the real one? Essentially 0. The same logic applies to universes. Bostrom concluded that at least one of 3 things must be true. Option 1. Civilizations like ours almost always go extinct before they develop the technology to create these simulations. Maybe nuclear war, climate change, artificial intelligence gone wrong, or something we have not even thought of wipes out advanced civilizations before they can reach that level of technological development. Option 2. Advanced civilizations that could create these simulations choose not to. Maybe they find the idea unethical. Maybe they are simply not interested. Maybe there is some universal law or agreement that prevents such simulations from being created. Option 3. We are almost certainly living in a simulation right now. Notice that Bostrom is not saying we definitely live in a simulation. He is saying that one of these 3 options must be true, and there is no obvious reason to prefer one over the others. If you think humanity will survive long enough to develop this technology, and you think at least some advanced civilizations would choose to run such simulations, then you are essentially forced to conclude that we are probably in a simulation. This argument shook a lot of people. It is not based on mysticism or wishful thinking. It is based on logic and probability, and that makes it much harder to dismiss. Let us dig deeper into this probability argument, because it is really the heart of the modern simulation hypothesis. And I want to make sure you understand just how unsettling these numbers are. First, let us think about how many simulations an advanced civilization might be able to run. Our current computers can already simulate simple systems with impressive accuracy. We can simulate the behavior of molecules, the flow of fluids, the movements of galaxies. And our computers are, in the grand scheme of things, still pretty primitive. Now, there is something called Moore's Law, named after Gordon Moore, one of the founders of Intel. Back in 1965, Moore observed that the number of transistors on a computer chip, which roughly corresponds to computing power, was doubling about every 2 years. And remarkably, this trend held true for decades. Let me put this in perspective. The smartphone in your pocket right now has more computing power than all of NASA had when they sent humans to the moon. And that was only about 50 years ago. Imagine what computers might look like in another 50 years, or 100, or 1,000. Some researchers have tried to estimate the computing power that would be needed to simulate an entire universe with conscious beings. A physicist named Seth Lloyd calculated that a computer the size of a small laptop could in principle simulate the entire history of our universe if it operated at the fundamental limits of physics. The simulation would have to be somewhat simplified, but it would be good enough to fool the inhabitants. Other estimates are more generous. By a civilization that has harnessed the energy of an entire star, something called a Type 2 civilization on the Kardashev scale, could potentially run billions or trillions of detailed simulations simultaneously. Now, let us do some simple math. Suppose advanced civilizations across the universe collectively run 1 trillion simulations. That is a 1 followed by 12 zeros. And suppose there is just one real universe. That means for every real conscious being, there are 1 trillion simulated conscious beings. Your odds of being in the real universe, the one base reality, would be about 1 in 1 trillion. Those are not good odds. You would have a better chance of winning the lottery multiple times in a row. But wait, it gets worse. What if the simulations can themselves create simulations? What if there are simulations running inside simulations running inside simulations? Each layer multiplies the number of simulated beings. The real universe becomes an infinitesimally tiny fraction of the total number of conscious experiences. Some philosophers call this the simulation stack. At the bottom, maybe, there is one true base reality. But above it are countless layers of simulations, each containing beings who believe their reality is the real one. Most conscious beings in this scenario would not just be in a simulation. They would be in a simulation of a simulation of a simulation. The math is inescapable unless something prevents advanced civilizations from creating these simulations. The probability that any given conscious being is in base reality approaches zero. We would almost have to be in a simulation. Now, I know what you might be thinking. Maybe this logic is flawed somehow. Maybe there is something wrong with the assumptions. And you are right to be skeptical. But here is the thing. No one has been able to definitively disprove this argument. The best critics can do is argue about the assumptions, about whether consciousness can really be simulated, about whether civilizations would really choose to create these simulations. But even the skeptics admit that if the assumptions hold, the conclusion follows. And that is deeply unsettling. To really understand why the simulation hypothesis has gained so much traction in recent years, we need to appreciate just how rapidly computing technology has advanced. Because the better our computers get, the more plausible the idea of a simulated reality becomes. Let us start with a brief history. The first electronic computers were built in the 1940s. They filled entire rooms, weighed several tons, and had less computing power than a modern calculator. The ENI AC, one of the first general-purpose computers, could perform about 5,000 operations per second. That seemed incredible at the time. Today, the latest computer processors can perform trillions of operations per second. That is an improvement of roughly 1 billion times in less than 80 years. If car technology had improved at the same rate, you would be able to drive to the moon in about 5 seconds for the cost of a cup of coffee. But raw processing power is only part of the story. We have also made huge advances in how efficiently we can simulate things. Video game graphics from 20 years ago look laughably primitive compared to modern games. The characters move more realistically. The physics are more accurate. The worlds are more detailed. And we are starting to see simulations that are genuinely convincing. Virtual reality headsets can now trick your brain into believing you are somewhere else. Deepfake technology can create videos of people saying and doing things they never did. AI can generate realistic images of people who do not exist. Our simulations are getting better at an exponential rate, and we are still in the early days. Imagine what simulations might look like in 100 years, 1,000 years, 1,000,000 years. At some point, they would be indistinguishable from reality, at least to the beings inside them. There is a concept in technology called the uncanny valley. It describes the unsettling feeling we get when we see robots or computer animations that look almost but not quite human. The small imperfections make them creepy. But here is the thing. The uncanny valley is a temporary phenomenon. As our technology improves, we will eventually cross the valley. Our simulations will not look almost human. They will look perfectly human, and eventually even better than human. Now think about what this means for the simulation hypothesis. We are already on a trajectory toward creating convincing simulated realities. If we continue on this path, and there is no obvious reason why we would not, then we will eventually be able to create simulations that are indistinguishable from base reality. And if we can do it, presumably other civilizations in the universe can too. Some of them might be millions of years ahead of us. They might already have this technology. The more you think about our technological trajectory, the more the simulation hypothesis starts to look not just possible, but likely. We are essentially proving that creating convincing simulated realities is achievable. And once something is achievable, the probability game starts to tip against base reality. Now, let us talk about something that physicists themselves find deeply strange: quantum mechanics, and how some of its weirdest features seem to align disturbingly well with what we would expect if we were living in a simulation. First, a bit of background. Quantum mechanics is the branch of physics that deals with the smallest scales of reality: atoms, electrons, photons, the stuff that everything else is made of. And at this scale, things behave very differently from what our everyday intuition would suggest. One of the strangest aspects of quantum mechanics is something called the observer effect. In certain experiments, particles seem to behave differently depending on whether or not they are being observed. Before you look at them, they exist in what physicists call a superposition, a kind of blurry state where they are doing multiple things at once. But the moment you observe them, they snap into a definite state. The classic example is the double-slit experiment. When you fire particles like electrons or photons at a barrier with two slits in it, they create an interference pattern on a screen behind the barrier. This pattern only makes sense if each particle is passing through both slits at the same time, like a wave would. But here is where it gets bizarre. If you set up a detector to watch which slit each particle goes through, the interference pattern disappears. The particles start acting like little balls, passing through one slit or the other. The mere act of observation seems to change their behavior. Now, why would observation matter? In the natural world, we know things exist whether or not we are looking at them. A tree does not stop being a tree when no one is in the forest. But in quantum mechanics, observation seems to be special. Reality seems to depend on whether or not it is being measured. Some people have pointed out that this is exactly what you would expect in a simulation designed to conserve computing power. Think about how video games work. When you are playing a game, the graphics in front of you are rendered in full detail. But what about the areas you cannot see? What about what is happening behind you, or in a distant part of the game world? Most games do not bother rendering those areas in detail until you look at them. It would be a waste of processing power. Could quantum mechanics be evidence that our universe works the same way? Could reality only be fully rendered when someone is looking? The parallels are unsettling. There is another quantum phenomenon that is relevant here: quantum entanglement. When two particles become entangled, they develop a connection that transcends space. If you measure one particle and find it in a certain state, the other particle will instantly be in a corresponding state, no matter how far apart they are. even if they are on opposite sides of the universe. Einstein famously called this spooky action at a distance because it seemed to violate everything we know about how the universe should work. Information cannot travel faster than light. So how can two particles communicate instantaneously across vast distances? One explanation that has been proposed is that entangled particles are not actually communicating. Instead, they are both part of the same underlying data structure, like two cells in a spreadsheet that are linked by a formula. Change one, and the other updates automatically, not because information traveled between them, but because they were never really separate to begin with. If the universe is a simulation, entanglement makes perfect sense. The particles are just variables in a program. They appear to be in different places, but in the underlying code, they are connected. The distance between them is an illusion, a feature of the user interface rather than the actual programming. Now, I want to be careful here. I am not saying that quantum mechanics proves we are in a simulation. Physicists have other explanations for these phenomena that do not require simulation. But I am saying that the weirdness of quantum mechanics is at least consistent with the simulation hypothesis, and that is more than a lot of people expected. Here is another piece of the puzzle that makes simulation theorists raise their eyebrows. The universe appears to be That is a fancy way of saying that at the smallest scales, everything comes in discrete chunks rather than continuous streams. Let me explain what I mean. In our everyday experience, things seem smooth and continuous. When you walk across a room, you do not jump from point to point. You glide smoothly through space. When you pour water, it flows in a continuous stream. But zoom in far enough, and this smoothness breaks down. Energy, for instance, does not come in any amount you want. It comes in specific packets called quanta. Light is not a continuous wave. It is made of individual particles called photons. Matter is not infinitely divisible. It is made of atoms, which are made of smaller particles. Even space and time might be quantized. There is a smallest meaningful length called the Planck length. It is mind-bogglingly tiny, about 1.6 times 10 to the negative 35 meters. Below this scale, our current understanding of physics breaks down. Many physicists believe that space itself might be granular at this level, like a fabric woven from incredibly fine threads. Similarly, there is a Planck time, the smallest meaningful unit of time. It is about 5.4 times 10 to the negative 44 seconds. Below this duration, time, as we understand it, might not make sense. Now think about digital systems for a moment. Your computer screen is not actually showing you smooth, continuous images. It is showing you pixels, tiny, discrete dots of color that are so small your eye blends them together. Digital music is not actually a continuous wave. It is a series of discrete samples, measurements taken thousands of times per second. Digital systems are inherently quantized because that is how digital information works. Everything has to be broken down into discrete units. And here we are, discovering that the universe itself seems to work the same way. Is this a coincidence? Maybe. Or maybe the universe is quantized because it is running on some kind of digital substrate. Maybe the Planck length is the resolution of the simulation. Maybe the Planck time is the tick rate, the smallest step forward that the simulation takes. There is even a speculative idea called digital physics, which proposes that the universe is fundamentally computational, that, at its deepest level, reality is information being processed according to rules, essentially a program running on some cosmic computer. Proponents of digital physics point out that many of the laws of physics can be expressed as information processing rules. The behavior of particles, the evolution of the universe, even the arrow of time itself can all be described in computational terms. Of course, this does not prove anything. The universe might be quantized for reasons that have nothing to do with simulation, and digital physics is still a minority view among scientists. But the fact that our best descriptions of reality keep looking more and more like computer code is, at the very least, interesting. Here is something that has puzzled scientists and philosophers for centuries. Mathematics works way too well at describing the universe, and this might be telling us something profound about the nature of reality. In 1960, a physicist named Eugene Wigner wrote a famous essay called "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." In it, he expressed amazement at how well mathematics, an abstract creation of the human mind, describes the physical world. Think about it. Mathematical equations, which are basically just relationships between abstract symbols, can predict the behavior of the universe with incredible accuracy. Einstein's equations predicted the existence of black holes and gravitational waves decades before we detected them. Quantum mechanics equations predicted the existence of particles that were only discovered years later. Why should this be? Mathematics is something humans invented or discovered, depending on your philosophical stance. It started with basic counting and measuring, but then it developed into these incredibly abstract structures that somehow turn out to perfectly describe the behavior of quarks and galaxies and everything in between. Wigner called this unreasonable because there is no obvious reason why a monkey's brain, which is what we evolved from, should be able to create tools that unlock the deepest secrets of the cosmos. It is almost too good to be true. Now, the simulation hypothesis offers an interesting explanation for this mystery. If the universe is a simulation, then it would be built according to mathematical rules. The programmers would have written equations that govern how everything behaves. And when we discover those equations, we are essentially reverse engineering the source code. Of course, mathematics works perfectly to describe the universe. The universe is mathematics. It is a mathematical structure running on some computational substrate. Our scientific discoveries are not learning about an independent reality. They are uncovering the rules that were programmed in from the start. There is a physicist named Max Tegmark who takes this idea even further. He has proposed what he calls the mathematical universe hypothesis, which says that our universe is not just described by mathematics. It is a mathematical structure, nothing more and nothing less. Every physical object is, at its core, a mathematical pattern. Tegmark's idea is controversial. But it has gained attention because it explains the unreasonable effectiveness of mathematics so neatly. If the universe is mathematics, then of course mathematics describes it perfectly. It is describing itself. Whether or not Tegmark is right, the mathematical nature of physical law is striking. We live in a universe that seems to follow rules, exact and precise rules that can be written down. This is exactly what we would expect if we were living in a programmed simulation. It is not proof, but it is consistent with a hypothesis. Let us talk about one of the most famous numbers in physics, the speed of light. About 299,792,458 meters per second. Nothing can travel faster than this. It is a fundamental limit of our universe. But here is a question that does not get asked often enough. Why? Why is there a speed limit at all? And why is it specifically this number? In most video games, there are limits on how fast objects can move. This is partly for gameplay reasons, but it is also for computational reasons. If things could move infinitely fast, the game would have to calculate an infinite number of interactions, which would crash the system. Similarly, in a simulated universe, you would want a speed limit. It would help keep the computational requirements manageable. Information about events could only spread so fast, which would limit how quickly different parts of the simulation could affect each other. The speed of light in our universe plays exactly this role. It is not just a speed limit for physical objects. It is a speed limit for information itself. Nothing, not matter, not energy, not information, can travel faster than light. This means that events in one part of the universe cannot instantly affect events in distant parts. There is always a delay. From a computational perspective, this is very convenient. It means the simulation can process different regions semi-independently. It does not have to constantly synchronize the entire universe at every moment. The speed of light creates a kind of built-in lag that makes the simulation more manageable. Of course, there could be other explanations for the speed of light. It might just be a fundamental feature of space-time with no deeper cause. But it is interesting that this feature is exactly what you would want if you were designing a simulation. Now we enter murkier territory, the realm of personal experiences and anecdotes. Things that feel like evidence to those who experience them, but are impossible to verify scientifically. I am talking about what some people call glitches in the Matrix. You have probably heard of the Mandela effect. It is named after Nelson Mandela, the South African leader. Many people clearly remember learning that Mandela died in prison in the 1980s. They remember seeing news coverage of his funeral. The only problem is that Mandela did not die until 2013. He was released from prison in 1990 and went on to become president of South Africa. How can so many people share such a specific false memory? Skeptics say it is just a quirk of how memory works. We confuse things. We fill in gaps with false information. We are influenced by what others say they remember. But believers in the simulation hypothesis have another explanation. What if these are not false memories at all? What if they are memories of a different version of the simulation? What if the simulators sometimes make changes, patch the program, edit history, and some people retain faint memories of how things used to be. There are countless examples of the Mandela effect. Many people remember the Berenstain Bears being spelled Berenstain Bears. Many remember the Monopoly Man having a monocle. He does not. Many remember a movie called Shazam, starring the comedian Sinbad as a genie. No such movie exists. Again, these can all be explained by the fallibility of human memory. Our brains are not video recorders. They reconstruct memories each time we recall them, and errors can creep in. The fact that many people make the same errors might just reflect common patterns in how our brains process information. But for those inclined to believe in the simulation hypothesis, these experiences feel like something more. They feel like glimpses behind the curtain, like moments when the machinery of reality briefly became visible. There are more dramatic examples too. People report strange experiences that seem to defy normal explanation. Objects that disappear and reappear. Doppelgangers spotted in impossible places. Time seeming to skip or repeat. These experiences are dismissed by mainstream science as misperceptions, delusions, or fabrications. And in many cases, that is probably exactly what they are. But in a simulated universe, such glitches would be expected. No program is perfect. Software has bugs, and the more complex the software, the more opportunities there are for things to go wrong. A simulation as complex as an entire universe would surely have occasional errors. The question is whether we would notice them, and what they would look like if we did. I want to be clear that I am not presenting these anecdotes as evidence. They are not. Science requires controlled, reproducible observations, and glitch reports do not meet that standard. But they are worth mentioning because they shape how people think about the simulation hypothesis. For many, these experiences are what first sparked their interest in the idea. Almost everyone has experienced déjà vu at some point. That uncanny feeling that you have lived through this exact moment before. That everything happening right now, the sights, the sounds, the words being spoken, has already happened in some previous life or previous timeline. The scientific explanation for déjà vu involves memory processing. Sometimes the brain accidentally files a new experience as an old memory, creating the sensation that the new experience is familiar. It is a kind of neural hiccup, a miscommunication between different parts of the brain. But let me offer an alternative interpretation that fits the simulation hypothesis. What if déjà vu is the result of the simulation running the same scenario multiple times? Like a video game player replaying a level to get a better score. Imagine the simulators are testing different outcomes. They run a scenario, observe the results, then rewind and run it again with small variations. Most of the time, your consciousness would be reset along with everything else. But occasionally, some faint trace of the previous run might persist, a ghost in the machine. And that ghost might manifest as the unsettling feeling that you have done this before. This is pure speculation, of course. There is no scientific evidence for it, but it shows how phenomena that seem mysterious might be explained if we are willing to entertain the simulation hypothesis. Déjà vu becomes not a brain glitch, but a feature of the simulation itself. The same applies to dreams. We spend roughly a third of our lives in a dream state, experiencing realities that feel completely real while we are in them. Then we wake up and realize it was all in our heads. Dreams show that our brains are capable of generating convincing simulated realities. What if waking life is just another layer of the same process? In recent decades, some physicists have started to think about the universe in terms of information rather than matter and energy. And this shift in perspective has some interesting implications for the simulation hypothesis. It started with black holes. In the 1970s, physicist Jacob Bekenstein discovered that black holes have entropy, which is a measure of disorder or information. And remarkably, the entropy of a black hole is proportional not to its volume, but to the area of its surface. This was strange. If you have a box full of gas, the amount of information needed to describe all the gas particles scales with the volume of the box. More space means more particles, means more information. But black holes do not work this way. Their information content is encoded on their surface, not in their interior. This led to an idea called the holographic principle. It suggests that all the information in any region of space can be represented as a kind of hologram on the boundary of that region. The three-dimensional world we experience might be a projection from a two-dimensional surface. If this sounds abstract, think about it this way. A hologram on your credit card is a flat two-dimensional surface that encodes three-dimensional information. When you look at it from different angles, you see different views of a three-dimensional image. The holographic principle suggests that the entire universe might work the same way. What we experience as three-dimensional space might be a projection from a lower-dimensional surface. This is mind-bending stuff, and it is taken seriously by mainstream physics. And it connects to the simulation hypothesis in an interesting way. If the universe is fundamentally a hologram, then the amount of information it contains is much smaller than you might expect. This makes simulating it more computationally feasible. There is another connection between physics and information that is worth mentioning. John Wheeler, one of the most important physicists of the 20th century, proposed a concept he called it from bit. The idea is that every particle, every field, every physical entity ultimately derives its function, its meaning, its very existence from information. Wheeler imagined the universe as a kind of cosmic computer with physical reality emerging from underlying bits of information. He saw physics not as the study of stuff, but as the study of information processing. If Wheeler was right, the distinction between physical reality and simulation might be less meaningful than we think. If reality is information, then a sufficiently detailed simulation would not just represent reality, it would be reality. So far, we have talked about arguments and evidence that are consistent with the simulation hypothesis. But can we actually test whether we are in a simulation? Can we design experiments that would give us a definitive answer? Some scientists have proposed ways to look for signatures of simulation. The basic idea is that any simulation would have limitations, and those limitations might leave observable traces. One proposal involves looking at the highest energy particles in the universe, cosmic rays. These are protons and other particles that have been accelerated to enormous energies by violent cosmic events. When they hit our atmosphere, they create showers of secondary particles that we can detect. There is a theoretical maximum energy that cosmic rays should be able to reach, called the GZK cutoff. This limit exists because high-energy particles interact with the cosmic microwave background radiation, the leftover glow from the Big Bang, above a certain energy. Particles should be unable to travel far without losing energy to these interactions. Interestingly, this is exactly the kind of limit you would expect in a simulation. The simulator might impose energy limits to keep the physics manageable. If we found that the universe had artificial-looking cutoffs or constraints, it might suggest we are in a simulation. Another proposal involves looking for patterns in the distribution of matter and energy that would suggest computational processing. If the universe is rendered in chunks or processed in discrete steps, there might be subtle patterns or artifacts in the cosmic microwave background or the distribution of galaxies. A team of physicists at the University of Washington proposed looking for specific lattice structures in the energy distributions of cosmic rays. The idea is that if space-time is simulated on a lattice, a kind of three-dimensional grid, the grid structure might affect how high-energy particles behave. So far, these tests have not found any clear evidence that we are in a simulation, but they also have not ruled it out. The absence of evidence is not evidence of absence, as scientists like to say. A sufficiently advanced simulation might be designed to avoid leaving detectable traces, and this raises a troubling possibility. What if there is no way to test the simulation hypothesis? What if we could never know, even in principle, whether we are in a simulation? This would not mean the hypothesis is wrong. It would just mean it is an unfalsifiable hypotheses occupy a strange space in science. They are not necessarily wrong, but they cannot be proven right either. Assuming for a moment that we are in a simulation, who created it? What kind of beings would have the power and motivation to simulate an entire universe? The most common answer among simulation hypothesis supporters is that the simulators are our own descendants, future humans, or whatever humanity evolves into, who have developed the technology to simulate their ancestors. Why would they do this? Maybe to study history. Imagine you wanted to understand how World War II really unfolded. Not just from documents and records, but by watching it happen in real time. You could simulate the entire period with conscious beings living through it and observe. Or maybe for entertainment. We already create simulated worlds for fun in video games. Future beings might create entire simulated universes the way we create video game levels. Or maybe for research. Scientists might want to test different initial conditions for the universe, different physical constants, to see what kinds of worlds develop. They might run countless simulations with slight variations to understand the principles of cosmic evolution. But future humans are not the only possibility. The simulators could be beings from elsewhere in our universe. An alien civilization that developed technology millions or billions of years ahead of us. Or the simulators could be something entirely outside our understanding. beings that exist in a reality so different from ours that we cannot even conceive of their nature. We might be to them what the characters in a video game are to us, made in their image in some abstract sense, but fundamentally different in nature. This brings us to some uncomfortable questions about the nature of the simulators. Are they benevolent, indifferent, malevolent? If we are in a simulation, our entire existence is at the mercy of beings whose intentions we cannot know. They could shut down the simulation at any moment. They could alter our memories, change the laws of physics, delete us from existence. We would have no way to resist or even to know it was happening. For some people, this is the most disturbing aspect of the simulation hypothesis. Not that reality might be fake, but that we might be completely powerless within it. Our sense of agency, our belief that we control our own lives, could be entirely illusory. At this point, you might be wondering whether any of this matters. Even if we are in a simulation, what difference does it make? The pain still hurts. The joy still brings joy. The people we love are still worth loving. This is a fair point, and many philosophers would agree with it. The practical implications of the simulation hypothesis might be minimal. Whether or not our universe is simulated, we still have to live in it. We still have to make choices, build relationships, pursue goals. But there are some ways that taking the simulation hypothesis seriously might change how we think about things. First, there is the question of meaning. For many people, meaning comes from the belief that their actions matter, that they are shaping a real world with real consequences. If the world is a simulation, does that change? Are our achievements less meaningful because they happen in a simulated environment? Philosophers have debated this, and the answers vary. Some argue that meaning is intrinsic to the experience itself. A simulated life can be just as meaningful as a real one because meaning comes from within, not from external validation. Others argue that being in a simulation would fundamentally undermine the significance of our choices. Then there is the question of ethics. If we are in a simulation created by future beings, do we have ethical obligations to them? And do they have ethical obligations to us? Is it ethical to simulate conscious beings who can suffer? Is turning off a simulation equivalent to killing the beings within it? These questions might seem abstract, but they become very practical if we ourselves develop the ability to create simulated consciousness. Are we morally obligated to treat simulated beings with the same respect we give real ones? What even is a real being if reality itself might be simulated? Finally, there is the question of how we should behave if we suspect we are in a simulation. Some tech billionaires have reportedly funded research into breaking out of the simulation. But would that even be desirable? What lies outside might be far worse than what lies within. Others have suggested that if we are in a simulation, we should try to be interesting to the simulators. Make sure they want to keep watching. Do not give them a reason to shut us down. This is mostly said in jest, but there is a kernel of genuine uncertainty behind it. One of the most interesting aspects of the simulation hypothesis is how it connects to ancient religious and philosophical ideas. In some ways, it is a modern, technological version of ideas that humans have been grappling with for millennia. Many religions teach that there is a reality beyond what we can perceive, that this physical world is temporary or illusory, and that a greater truth lies beyond. The simulation hypothesis says something similar. This physical world is not fundamental. It is a construct generated by something outside our experience. In Hinduism, there is the concept of Maya, the illusion of the physical world. The material universe is seen as a kind of cosmic dream, and enlightenment involves waking up from this dream to perceive the true nature of reality. In Buddhism, there is similar skepticism about the reality of the physical world. The world we perceive is shaped by our minds, our desires, our attachments. True understanding comes from seeing through these constructions. In Gnosticism, an ancient religious tradition, the material world was seen as a kind of prison created by a flawed or malevolent creator. The true divine reality lay beyond this material realm. Salvation involved escaping the material world and ascending to the true spiritual reality. These ideas parallel the simulation hypothesis in striking ways. The physical world is not ultimate reality. There is something beyond. Our task might be to understand our true nature and transcend our current limitations. Of course, there are important differences. Ancient religious traditions typically framed these ideas in spiritual or metaphysical terms. The simulation hypothesis frames them in technological terms, but the underlying intuitions are remarkably similar. Some people find this connection comforting. It suggests that the questions raised by the simulation hypothesis are not new, and humans have found ways to live meaningful lives while grappling with them. Others find it troubling. If the simulation hypothesis is just ancient mysticism dressed up in technological language, maybe it is not as scientific as it appears. What strikes me most is how the idea keeps popping up in different forms. Plato imagined it as shadows on a cave wall. Descartes imagined it as an evil demon. Eastern religions imagined it as cosmic illusion. And now we imagine it as a computer simulation. The specific metaphors change with the times, but the underlying question persists. Is reality what it appears to be? Or is there something more? Something hidden, something beyond what we can perceive? Let me leave you with this thought. Whether or not we are in a simulation, the fact that we can ask the question is remarkable. We are conscious beings in a vast cosmos, trying to understand our own nature and the nature of reality. That quest for understanding is, perhaps, the most human thing about us. And if it turns out that we are just patterns of information in some cosmic computer, well, we are patterns that think, that feel, that wonder, that has to count for something. Sleep well tonight, if you can.